Welcome to this special Center session of Shadow the Scientist, Astronomy Night at the International Gemini Observatory North. My name is Jamika Marshall, and I am pleased to serve as the coordinator for the Shadow the Scientist initiative. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located in Hawaii and Chile. The 8-meter primary mirrors are coated with protected silver for infrared optimization. Diverse and on-demand instrumentation allows for efficient observation modes, which switch from observing planets in our solar system to looking into the depths of our universe in just a few minutes. Now, Gemini excels in the search for and characterization of exoplanets. Adaptive optics technology actually removes the distortion caused by the Earth's atmosphere so we get ultra-high resolution astronomy. Now, Gemini telescopes use laser guide stars to expand the capabilities of adaptive optics systems. And their staff in both hemispheres coordinate daily and nightly observations and maintain those scientific instruments. Staff is recruited locally throughout Gemini's international participants and beyond. The Gemini International Partnership includes the US, Canada, Chile, Brazil, Argentina, and Korea. The host communities in Hawaii and Chile benefit from local outreach programs that engage students as well as the public. Now, from the cores of active galaxies to exploring worlds around other stars, Gemini Observatory is committed to exploring the universe and sharing its wonders with all of humanity. The Shadow the Scientist team here at Gemini Observatory North is led by Dr. Brian Lemo. Brian, how are you?
Aloha, Jamika. I'm doing well. How are you?
Fantastic. I am thrilled to be here with not only all of you in the control room, but all of these amazing teachers and their classrooms. So why don't we segue over to you to start introductions for you and your team. I'm going to mute myself and join you in the control room.
Okay, sounds great. Aloha, everybody. My name is Dr. Brian Lemo, as Jamika said. I'm a staff scientist here at Gemini North International Observatory in Hilo, Hawaii, on the Big Island of Hawaii. As Charlie mentioned in our chat, we're actually sitting at about sea level right now. So we are in our base facility. And this is where we do most of our observing from. And we are robotically controlling the telescope up on the summit of Maunakea, which is about 4,000 meters. So what you see behind us is all these different computers that allow us to interact with the telescope up at the mountain, and where we take all of our astronomical observations at 4,000 feet. And so my role here at the observatory is to get the most out of the nights that we have open. And so to take all of the wonderful ideas from scientists all over the world and transform them into wonderful observations with our wonderful telescope and get some amazing science out. So I've been here for about 2.5 years working at the Gemini Observatory. I come originally from California on the mainland. And I come from academia. So I was a scientist at the University of California, Davis, for many years. I was also a postdoc in Marseille in the south of France for 4 years. But in those places, I use telescopes. I use telescopes on Mauna Kea and all over the world. But I only got to do that about I would say 4 or 5 nights per year if I was really lucky. So it's really hard to get time on these very, very large telescopes. It's very competitive. You have to have great ideas and everything has to go right for you to observe. Here at Gemini, I can be a part of observations 365 nights a year. And in fact, we have a twin in the south at Cerro Pachón in Chile. And so we have two telescopes looking at both hemispheres every night that conditions allow for it. And so it's a very, very exciting opportunity. I love working here. I love seeing all the wonderful science that's being done here from not only things that I'm interested in, but all over the universe. And so any given night, we can observe anything in the universe if we're open. Yeah, so that's kind of what I do here. We have other people in the control room that may want to introduce themselves and give a little bit about their background and what their role is. So I'll pass to Charlie, maybe. Charlie's our observer for this evening.
I am. My name is Charlie Figuera. I am a science operations support specialist or something like that. Among my roles are to operate the telescope, to safeguard the telescope's safety in terms of weather and any other conditions that might arise, to address faults or problems that come up. And as observer, I actually direct the instruments and conduct the observations that these researchers from around the world have asked us to help them with. So I spend a lot of my work here as part of the night crew, staying up all night long until dawn to collect that data. I spent years I've been here at Gemini for about 3 years now. Before that, I was also in academia. I taught physics and astronomy and did research as a radio astronomer studying high mass star formation. And I think as Brian said, it's a big change to go from the situation where we are working with the telescope for a few nights a year, a week or two a year, to getting to do this all the time. Zach?
All right. Hey, everybody. My name is Zach Hartman. I am a science fellow here at Gemini. I was born in Michigan and eventually made my way across the mainland over to Hawaii, first in Atlanta, then Flagstaff, and now out to here. So it's been the steady journey across the US.
Westward.
Yeah, westward across the US. So my position is a postdoc, as Brian mentioned, at being one in France. And so mine is a temporary position. So I've been here about as long as Brian, 2.5 years. So eventually I will have to begin searching for another job. But
Zach.
I know, it's so sad. But my job is very similar to Brian's. I help out setting up people's programs, making sure that the other scientists who apply for Gemini time and get Gemini time, their proposals and their programs are completed successfully. And I also do my own research. I focus a lot on speckle imaging, which is one of the unique capabilities of Gemini, at least two of the instruments on there, where we take really short exposures and reach the diffraction limit of the telescope. So with that, we're able to resolve really, really close binaries, much like as Shamika mentioned in the introduction about adaptive optics, but this is using a different method. And yeah, so I think that's it from me. And so I'll turn it over to Grant.
Okay. Hi, everyone. This is Garima Singh, and I'm the adaptive optics scientist at Gemini. I joined Gemini about a year ago, and I am a project scientist for an instrument called Gemini Planet Imager. So it's an instrument which is going to take direct images of exoplanets. So these are the planets that orbit stars other than the sun. So my job is to make sure that the instrument is doing what it's supposed to do. And just to give a little bit of background about, well, my background, I come from the city of Haridwar, and I left India about 15 years ago for my master's. I did my master's and PhD in France and US, and then I worked as a postdoc fellow in France and Canada before joining Gemini. Nice to meet everyone.
Thank you, guys. Yeah, so as everybody mentioned, this is a very complex observatory. We have a lot of different partners that Jamika highlighted in her introduction. And even the telescope itself has many, many different instruments. And so as Charlie mentioned in the chat, on any given night, we have this, pool of scientific observations that we can take. We're, essentially shadowing the universe. So we're essentially seeing what we see, but we can have some idea beforehand. So scientists send us their ideas. We have some idea of what we might see. And so we set up the observations using this suite of instruments. So these instruments are attached to the telescope. So the telescope is just a giant light bucket, which then throws that light into the instrument of our choosing, and that instrument then does something. So Zach mentioned speckle. That's one type of way of manipulating the light. We have spectroscopy, we have imaging, we have polarimetry, or we'll have polarimetry at some point. And so, depending on the scientific question, we may choose to use different instruments. And so the scientists that have the ideas, that send us their ideas, and that are successful at getting time on the telescope, say, I would like to use a particular type of instrument, and then we focus the light from the telescope into that instrument and take an observation in order to test whatever theory they might have about a particular object in the sky. So we have phenomena that are very long-lived. So, typically galaxies don't change on human timescales. So somebody would make a proposal to say, hey, I'd like to look at that galaxy. I saw it with another smaller telescope, and I really want to get precise information on that galaxy. So can you do that? A year later, we take the observation, or 6 months later, or even a month later, we take that observation, and it's basically the same galaxy as when they proposed for it. But one of the neat things here at Gemini is that we have what we call target of opportunities. And so on any given night, if something goes bang in the universe, a scientist can send us a request to say, oh my gosh, there's a super exciting thing that just happened. Can you please, or you're contractually obligated, could you please go over to this particular object that I just saw go bang and take a look at that? And so I think Charlie might give us an example later this evening of when that happened a couple of years ago, and we were able to get the telescope on fast enough to take a really neat observation. So that'll be later in the session that will show data from supernova that occurred about a year and a half ago. So unfortunately tonight, it looks like we may not be observing the universe, or at least we'll be observing only the very, very local universe, by which I mean the summit of our mountain, because there are conditions, there are particular conditions that we need to adhere to safely open the telescope. And so currently tonight, the conditions are not good enough for us to open the telescope. And so we are currently in the unfortunate situation of only being able to analyze or look at previous data. And so we have a variety of different conditions conditions that are set for us to open our telescope and to start observing the universe. And I wonder if anybody in the chat might give us some ideas about what might cause an astronomical observatory to not be open. So what conditions, either in the sky or on the ground, might cause us to not be able to observe on a given night? Might anybody have an idea?
Ooh, it looks like we're getting some answers in the chat.
Poor visibility.
Okay.
We saw weather conditions. We saw dew. A dog.
Dog.
Oh, fog. Well, dogs too, I suppose, in the wrong place.
Yeah. It's a little tough for dogs at 4,000 meters.
4,000 meters
Yeah.
is hard on everybody, really.
Yeah. Mm-hmm. Yeah, so these are all great answers. Yeah.
Great
Yeah,
answers.
absolutely. So things happening up in the sky, things happening down the ground, fog, mist, light. Yeah, lights, certainly terrestrial lights. If somebody were to come shine a big light up there and we could
Good.
away from the telescope,
Dust.
it would be bad.
Just on the mirror.
Yeah.
Fireworks.
Pollution, yeah. Yeah. Yeah, we're also on an island that has several active volcanoes, and so that can potentially cause issues, not for the top of Maunakea, but there's sulfur dioxide that can definitely become a problem for us.
The nice thing is that our facility here, one of the benefits of our location is some of those things we don't have to worry about. Light pollution is usually not an issue, although we have had people over the New Year setting off fireworks up on the summit, which was
Really?
which was troublesome. Yes.
Oh gosh, okay.
Yeah. But usually light pollution and atmospheric pollution are less issues here than they might be in other places. That's part of why we're here, why this place is so special.
These are absolutely fantastic responses. Sorry, Charlie. I was trying to keep up with all of the answers. Yes, amazing, so fantastic, and I feel like maybe for this evening, they're kind of a conglomeration of multiple things happening.
Yeah. So the answer, I mean, besides dogs, the answer is really almost all of them.
Many of the things.
Many of the above. So currently, I think so. We have some cameras that are situated on the outside of our dome kind of structure up on Maunakea, and we might be able. Zach, maybe you could show with.
You turn on your camera.
Yeah, I think maybe just the camera.
Oh, I see what you're
Share
saying.
screen.
Yeah.
Cameras.
So we have some live cameras at the top of the summit and on our dome, which help us assess the conditions up there. And normally, if you look back at many of the previous Gemini North Shadow of the Scientist sessions, you'll see a beautiful sky up there. Maunakea is one of the best observing sites in the world. And so probably 70–80% of the time, it's a beautiful sky up there. But unfortunately, tonight, there is a lot of humidity. It's not actually that cloudy up there, but at 4,000 feet, there's fog, there's humidity, there's very high winds. And so we're dealing with some very poor conditions for this evening. And so
right now winds are gusting at 33 meters per second. They were up at 45, 46 about an hour ago. So it's very high winds, very high humidity, very unpleasant conditions up there right now.
And so if I may jump in right here, Charlie, Zach, Garima, and Brian, since things are closed and there's no observing tonight, would you typically still be here in the Hilo Base Facility? Do you have other duties you would need to tend to because the observatory would be closed?
It depends. It depends on if there's an observing deadline tomorrow or something like that. Yeah, so it depends on your role, really. So Charlie this evening is our observer. I mean, we all shift around roles, and Charlie this evening is our observer. So Charlie probably wouldn't be here. He would be getting some rest.
So what happens when we have weather conditions like this? Sometimes the night is called early. So today, for example, an email went out at about 3 o'clock in the afternoon, which was coincidentally just after I'd woken up and gotten into the shower to come into work tonight, saying that we were calling the night early. Often, past few nights, the weather conditions have been similar, not quite this bad, and we didn't call the night right away. And so the observer, the operator, the night crew, I'd be in here waiting, and there's many times where we've come in and And the situations have been poor weather to start with, but by midnight or maybe 1 or 2 in the morning, conditions improve enough that we can get on sky. And so we'll be here and we'll wait until those conditions improve. If we can look at the forecast and we are confident that the conditions will not improve, then we might call the night early. So a couple nights ago, we called the night at midnight and went on home then because it wasn't going to get better before dawn. So, and that's probably what happens most of the time. We don't call the night early very much. So while my colleagues here might all go home, the night crew will still be here waiting.
And even in the cases where we do call the night early, a lot of times we will still have telescope work. So there's plenty of things that happen at the observatory that's not just what happens at nighttime. So we have to prepare all the instruments to be ready for observing at nighttime. It may be that there's not enough time in the day to properly get all the instruments up and running. And so it perhaps at nighttime and at a time where we're closed, at least temporarily, we may stay here and do some what we call closed dome work. So basically just using a light source within the dome to calibrate some of the instruments so that we're more prepared if we happen to open up on that given evening to take the best advantage of the conditions that we have. And so there's a lot of things that happen behind the scenes at the observatory, which can happen still when we're closed dome and, we can't actually take astronomical observations.
Most of those things happen during the day. We try not to schedule those kinds of things in the evening, but sometimes they do happen.
Yeah. And so also many of the staff observe on other telescopes. And so Zach, you do a lot of observing in Arizona, right? Yep. And then also in Chile, I observe on many of the telescopes on Maunakea. And so it may be on a given night that I'm actually observing with another telescope on Maunakea that maybe have better conditions. So Maunakea is a very active environment. And so if I'm observing, for example, on the Keck telescopes, which is just to the northwest of the Gemini telescope, the conditions there could actually be quite a bit different than the conditions at Gemini. And so it may be that the Keck Observatory is open, Gemini is not, or vice versa. And so, there's very active research programs that are happening here as well. And a lot of that happens at night, although it's night, could be in Arizona, it could be in Chile where it's during the day for us, or it could be at nighttime in Hawaii. So yeah, it's kind of a 24-hour activity here. It's always night somewhere.
It's always night somewhere.
I like that. It is always night someplace. Well, I am just really thrilled that you all, even though the observing is actually canceled for the evening due to challenging weather, we are grateful that y'all still came in for this special session with these amazing teachers and their classrooms. Thank you all so much, because you certainly did not have to do that. So we're going to make the most of our experience and our time with you and jump into possibly some of these questions. I know that a little bit later, hopefully we can talk a little bit about some of the tools that are used when you're doing observing. And as Charlie, Brian, and Garima mentioned, and also Zach, we're going to look at some really special things later in the evening, like a supernova, and get some insight into how, if you were doing those observing, how you could take a look at the data to make sure it's exactly what you're hoping for. But before we do that, I'm going to scroll back up in the chat, and I'll open this up to everyone in the control room. We appreciate, first of all of your questions and comments. Thank you so much. Keep them coming. If for some reason we do not get to your question, we apologize. Just send me a little nudge in the chat, and I'll make sure that we'll go back and get to it. And Garima, Zach, Brian, Charlie are actually answering some of these questions right now. But let me just check really quickly to see if we've missed any. And while I'm checking the chat, if anyone joined after we did the introduction to the International Gemini Observatory, again, my name is Jamaica Marshall, and I am pleased to serve as the coordinator for the Shadow the Scientist initiative. And as our scientists were saying, they're in the control room behind me. I was going to go in, but there's a bit of a feedback for some reason, and I don't want to be. I don't want you to have to experience that. So I'm going to stay out here while they are right behind me, though. As we were saying earlier, if you just joined, we are experiencing some weather. So what that means is we get all of the attention of our astronomers this evening. This is a very special situation. And we have in the control room, Garima, Zach, Charlie, and Brian. All right, I'm going to mute for just a moment, check and make sure we're not missing any questions, and then we can jump back into conversation with our astronomers and potentially see how a night could go, what tools you would be using to get observations started.
I'm
just gonna check and see.
There's a question I would love to address.
Okay,
Can I go ahead and do that?
yeah.
So one of the questions,
for it,
actually
Charlie.
there's a couple of questions that asked about our facility here in relation to volcanoes and relation to earthquakes. And the answer is, yeah, both volcanoes and earthquakes do sometimes pose a problem. Maunakea itself is technically still active. It has not erupted in some 6,000 years, and it's quite stable. But we have 5 major volcanoes on the island, and 3 others are definitely active and have erupted much more recently than that. When we have eruptions, we have fairly regular eruptions of Kilauea. We had a once in several decade eruption of Mauna Loa, actually last November, December, or a year ago, November, December. And they can put a lot of ash into the air and other debris. And so we have to be very mindful of particulate dust material that can accumulate, as well as some other volcanic gases. So that's one of the things we have to worry about. And because of that volcanic activity, we do see fairly regular, it's not uncommon to have earthquake activity as well. And we'll feel those earthquakes in Hilo, and we can detect them in our sensors up at the summit. And in fact, by some regard, our equipment up there is some of the most sensitive seismometry equipment that you could find. It wasn't designed that way, but because it's supposed to keep be very good at watching a particular area on the sky, we can see the shake in the ground because that image will wobble. We won't be able to hold that image steady. And one of my favorite stories about this is actually just a few weeks ago, we had a magnitude 4.4 earthquake near Kilauea, which is about a half an hour's, 40 minutes drive away. We felt the shock here in the control room in Hilo, and then a few seconds later, about 10 seconds later, maybe not that much, we could hear that shock hit the summit of Maunakea, which is about 30 kilometers away. And so we have microphones in the dome that as operators, as observers, we're paying attention to, because sound can be a very good indication if something goes wrong. And so we could hear the dome shake. We could hear it flexing and rattling as it shook. And because of my own interest in geology, I could go back and calculate how fast that earthquake wave moved in the ground from here to there, and it matched up very well with what the propagation wave should have moved at through basalt lava, which is what the island is made of. So it was all kinds of science that night. Usually earthquakes don't shut us down. If it's a very strong shock, we might shut down until things can be checked. But that magnitude 4.4 shock is very, once things stabilized, we just went back to work. We had no problems. There were no interlocks, no faults that occurred. We just had to restart that observation because that shock essentially did spoil that particular observation we were on at the time. So they are interesting. They don't really cause us too much difficulty, fortunately.
Charlie, I had no idea that you all could feel it here.
Oh, yeah.
And
Very
then only
much.
a few seconds later, hear it.
That was the first, I feel like that was the first time that I actually happened to catch it that way. Some of the operators like to turn the mics down in the dome because particularly the cooling refrigerators there that provide coolant to the instruments have kind of a high-pitched whine, and that will annoy people. I like to keep it up when I am acting as operator. So Zach over in the corner here, that's our operator station. The observer station is right here where I'm sitting now. But when I'm operator over there, I like to keep the volume up a little bit higher because I'm listening for odd clunks or bangs or whines or other sounds that tell me that maybe some piece of equipment isn't working the way that it should. And I just happened to catch that when that shock hit us.
Amazing, Charlie. Absolutely amazing.
Sorry, good question.
Okay.
I'm gonna ask, explain steps, calibration, observation.
Cool.
Yeah.
That's a
question.
That's a big question. We have on the telescope at any given time at least 2 and up to 4, generally up to 4 instruments, I think, that are capable of making measurements. Some of those stay on the telescope all the time, some of those switch on and off. And in general, we try to make sure that every one of them is available for observation on a given night. One of the things that we do very well at Gemini is that we are very nimble. We can switch between different instruments. So we can switch from a infrared imager to a visible light spectrograph. We can switch to an infrared spectrograph. We can go back and forth between these different types of instruments that are good at making different types of measurements in very short order. Some of those it'll take a minute or so to switch from one instrument to the other. So we might have a researcher who wants to use several different instruments to study the same object in space just to get different pieces of information from it. So we have to calibrate each of those instruments every time we use them. We go through daily instrument checks. The day operator, who usually sits over here where Garima is sitting, they will run checks on the instruments every day that make sure that everything in the instrument is lined up correctly, that many of these instruments have a lot of moving parts. So we want to make sure that we know where those moving parts are, that they are indexed correctly so they can go exactly to the right spot every time. When we are on sky, when we're observing through the night, the observer will work from a set of plans that one of the astronomers has made during the day. That person is called the Q coordinator, and they basically set up, here is the possible lists of things that we could look at tonight. Here are the different research observations that are in our list, that are things that are going to be up in the sky as opposed to set below the horizon. They're going to be good to observe right now. And so the observer, me tonight, is going to look at that list. We're going to look at the weather conditions, clouds. We're going to look at sky brightness. Is it a full moon? Is the moon set? We're going to look at water vapor in the atmosphere. We're looking at a whole bunch of different parameters to figure out which of these observations we should do right now. And we want to always try to do the highest priority for those weather conditions. We'll send that observation over to the operator. They will slew the telescope. They'll move the telescope to that location. They'll set up guiding to make sure that it stays in the same place, zeroed in on that target for the CoreSat observation. And then my role as the observer is to actually make sure we're looking at the right target and start the observation. And then that process sort of keeps going on and on. And part of some of those observations are not just science observations where we're looking at the unknown thing, but we're looking at some known things. So for example, if we're doing spectroscopy, we'll look at a standard star whose spectrum is really well known, so we can make sure that we can calibrate the unknown spectrum that we got, compare that to the known thing we have. So there's a whole host of those kinds of calibrations that we do depending on what kind of observation we're making. And then the big job happens after that, when the researcher is going to take all of that data and what's called reduce it and analyze it, to basically process it to figure out the answer to the scientific question that they're trying to ask. Big question, but hopefully that's kind of a nutshell answer.
A lot of great questions here.
There are.
There are, and I'm looking around the room and all of my colleagues are busy typing answers.
It's like we're actually observing.
Yeah.
It is almost like that.
Observing while you all are answering questions, having had the privilege and honor of shadowing you all in other sessions, there are so many tools that you use when you are observing, and even to get prepared for observations. Someone asked earlier, what's being displayed on the screens, and we got some great responses there. But when you're actually doing observations, there are maybe a few really important tools that you use. Can anyone speak to that and maybe show us some? I see finger pointing. I'm not going to say anything else, but we appreciate. Anyone want to talk about like the observing tool?
Yeah, that would be a great idea. Let's take a trip down the observing tool. Let's do that. So the observing tool, that's like to do everything. So the observing. So what we do on a given night is observe the universe, and we observe it with our telescope, but we need pieces of software that help us interact with the telescope, interact with the scientists that have the ideas, so that we can make sure that the observations that we take are looking at the precise object that the scientist wants in the precise way that the scientist wants it, and for the exact amount of time that the scientist wants it. So a lot of the observations of the observatory are not observations that we take for our own scientific interests, although we all are able to propose for time on the telescope, but it's people from all over the world. Anybody in the world can apply to the Gemini Observatory, either Gemini North, Gemini South, or any of our NOAA lab telescopes. And then we take those observations here. And so, for example, my job and Zach's job is to help get scientific programs ready for nighttime action. So when we're open and we're able to observe that everything is exactly set up in the way that we want. So Charlie mentioned a lot about getting our instruments in the precise configuration that they're best able to utilize the light coming from the telescope, essentially, in a nutshell. And so our job similarly is to temper these scientific programs, create observations that meet the exact needs of the scientists, so that everything confluences to getting the most out of a given amount of time on sky. And so the tool that we use to do that is this observing tool here. And so maybe Jamika, you can pin my screen. So this would be the other screen. Yeah.
Oh, that's great. Okay. Perfect.
Yeah, that's the one.
This one, gotcha.
Yeah. So it may be a bit hard to see, but this is one of our control computers here. So where my hand is here. This is one of our control computers. So we have 4 control computers in the room. Charlie's on one, Zach's on another, Garima's on another. And this is, as Charlie mentioned, we have a lot of roles at the observatory. It may be that a given instrument needs to be looked at during daytime or nighttime. And so we have the instrument team on one computer. We have the operator on another computer. We have the observer on another set of computers. These are all mirrored instances, more or less, of the same types of software. And so we can all talk to each other in software space across the room. And this software is also mimicked up on the summit of Maunakea. And so this is our tool to get the scientific program ready and then to execute the observations that we want to take. And so this is just an example of something we might do. And so this is our interface here. And it has a bunch of different observations. So over here on the left of the observing tool are all different sets of observations. So each one of these consists of an instrument and an astronomical target. And so something in the sky that we want to point at, and the instrument that we want to use when we point at that object. And so for each instrument, there's a variety of different modes. We can take imaging, we can take spectroscopy. And so we set up within this program those observations, those modes, and then that's ingested into our telescope operations. And so Charlie, as the observer, after we get this program set up, we have the astronomical object that we want to point to, the mode set up, everything is correct for the observations. Then Charlie can simply grab that information and take the observation in the way that it was intended. And so this particular observation here is it a kind of boring patch of the sky, but somebody thought it was very interesting. So we have a particular instrument that is called GMOS, so Gemini Multi-Object Spectrograph. And let's see. So if you guys can see the image here, there's an astronomical source that's pointed at. You can't see it in the image, but this image is a fairly shallow image. So this was taken with a telescope that is much smaller than ours. And so the astronomical target is actually fainter than could be seen with that telescope, but with our telescope, we should be able to see it. And we put a slit on that astronomical target. And this instrument takes the light from the telescope. It then sends that light through this slit, then through a dispersive element, so creating diffraction, that breaks up the white light into its constituent colors, and then we measure a spectrum of that source. And so we use a variety of different let's say mechanical tools to ensure that we're in the right location, that we stay in the right location for the entirety of the observation. So this particular observation determined by the sequencer here. And in fact, this observation would be about an hour and a half long. And so the sky moves. We want to make sure that the telescope moves in the precise fashion to track the astronomical object that we're looking at. This slit is very, very small. So it's the size of the slit is 1 arc second, which is 1/3600th of a fingernail at arm's length up in the sky. So fingernail is 1 degree, 1/3600th of that is an arc second. So that's a very small angle on the sky. And we need to keep that astronomical object for an hour and a half within this very tiny slit. And so we use this wavefront sensor here to make sure that we're pointed in the precise location that we want to be, and that we track that bright star that the wavefront sensor is pointed at the entirety of the observation. And that ensures that we're getting the most light that we possibly can through this slit, and we're getting the most information possible from the scientific target. And so as ideas come into the observatory, so the general process is that people propose for time. About 20% of people that propose for time are granted time on the telescope. And at that point, when somebody successfully applies to the telescope, myself or Zach or other staff members will help get the observations ready through this tool. And then Charlie or myself or Zach or somebody else will then observe using this tool. And then we will pass those data to the scientists to then test whatever questions that they had, whatever reasons they had to take an observation with Gemini. So yeah, this is a fairly unspectacular portion of the sky, although there's plenty of things that can happen in unspectacular portions of the sky that are super interesting. Let's see, Charlie, which program is up there on your screen?
This guy?
Yep.
That's Q403, looking at the M81 bulge.
23. Okay, so I won't bring it up. But yeah, so probably in this particular program that I just showed you, this is looking at an astronomical object that's many billions of light years away. And so this is why it's not visible in the image. But we also look at things that are very nearby. So Charlie just mentioned that there's a program, in fact, a program that we usually would observe when it's cloudy out, looking at much closer, much brighter things. And so one of the amazing things about the Gemini Observatory, because we're sourcing all this science from all around the world, unlike other observatories that use what's called classical nights, where scientists show up at the observatory and they have one idea about what they're going to observe, and then if the conditions change, they just have to keep observing, maybe very distant objects or things that are not suited for the conditions. We actually switch based on the conditions what we're observing. So if things are cloudy, it makes it more difficult to see fainter things. We'll switch over to brighter targets. And then as the clouds abate, then we may switch back to deeper universe things. So this is it's a very adaptable observatory, and the observing tool is what we use to talk and set condition constraints and determine what's going to be observed next.
Someone asked about the mirror cleaning. There's so many amazing questions and answers going on. Thank you all so much. I'm glad that I can actually contribute to a few of these responses. And I'm dropping in the chat right now a short video showing the Gemini North mirror being cleaned, as Charlie and Garima were talking about. Drop that right now.
Yeah, you had an amazing explanation of the mirror cleaning last time. I guess that was our inaugural Gemini.
Oh yeah, so mirror cleaning, we typically, the number one rule is don't touch the mirror. Don't ever touch the mirror, ever. When we clean the mirror, we tip the telescope down to zenith. So basically the telescope is pointing straight across, which means the mirror is essentially oriented up and down. And our summit crew will get on a lift and use a carbon dioxide wand. So basically they're going to be using carbon dioxide to blow any little bits of dust off of the surface of the mirror. This is part of the reason why it's so important that we keep the telescope closed under high humidity, because if it's humid and we get dew on the surface of the mirror, then any dust that accumulates there will basically stick and it becomes much harder to get off. As long as we keep the mirror surface dry, then any dust is going to just be able to be blown right off. And yeah, there you can see in the video of our crew using these carbon dioxide wands to just blow anything off. The carbon dioxide is inert to the mirror surface, so it's not going to damage the mirror surface, and it's going to get that dust off of there. And the dust, of course, attenuates the signal, because if light hits the dust and not the mirror surface, it's not going to go into the instrument.
So as you were saying, Charlie, this kind of cleaning happens much more regularly.
It happens, ideally it happens every week. It's essentially scheduled to happen every week. It will get delayed if there is a lot of activity at the summit. If there's other things going on that are it's too busy. It's not the highest priority task. We don't like to go too long without it, but we will delay it. And of course, we will delay if humidity is high. Many times, there's been not a small number of times when I've been the day operator and the humidity is just too high. If it's at 80 or 90% humidity, they don't want to do anything with the mirror. We keep it covered, we keep it safe.
Covered and safe sounds like the way to go. Now, I'd like to share one more thing as we are still talking about mirror cleaning. This is a video, it's the Gemini South cleaning lab. What does the cleaning lab do? And it's the cleaning lab here. Look at this. Is this for cleaning parts of the instrument, or is this for?
So, yeah, you may want to
put it up there.
You may want to put up there.
Share.
That looks like their instrument lab. I'll be honest, I'm not entirely sure. I haven't seen this video before. It looks like that's basically Gemini South and Gemini North are more or less mirror twins. They're not entirely, they have some slightly different facilities to their support building than we do. But that looks very much like the instrument lab. So you can see there's a high bay crane in there, a hoist that they can lift things with. But that looks like their instrument lab.
Okay, all right. I was trying to find one more. There was one video that I remember showing before when you were talking about mirror cleaning in the inaugural Gemini shadow session.
Which also was weathered out. I'm starting to think I'm bad luck.
Oh my goodness, I hadn't thought about it like that. No, you're not bad luck. Y'all are the best luck because you are allowing us to be with you, shadowing your work, even though you don't have to be here this evening. They joined just for us, just for you, just for all of you. And so we're absolutely grateful. All right. Let me get back to looking at questions. I'm going to stop talking. Observing tool and things.
So it's kind of, it might be interesting just to see what our workstation looks like. Jamika, if you can show your camera here.
Remove your pen, Brian.
Yep.
I'm going to turn on my camera.
Turn on your camera. So, hi, up close and personal. So I'm going to just adjust a little bit here. So this is the observer workstation. The workstation consists, I'm going to aim you just a little bit. This is the main workstation. It's a mirror of the one over on the other side of the room, actually of the one over that Garama is at as well. 8 monitors, 8 fairly large monitors. We probably have some, I don't know, 30, 50 different applications, windows that are up. And probably one of the most intimidating things when I first started training here was just trying to keep track of everything and to know that I would be able to keep track. But basically, we are looking at telescope conditions over here. What is a telescope actually doing? I have some weather plots over here. The humidity plot is not interesting because it's all at the 100% line right now. This shows me telescope guidance. Since we're not observing tonight, there's no guidance going on. I can look at our Q plan. So basically all of the available observations over the course of the night. So this is a stretch of nighttime. This is actually from last night when I was observing. And so each of these green and yellow slices represents a program that's going to be observed. So here is a program that was going to take about 3 hours to observe, and then some shorter 1 hour, and then some ones that are even shorter than that. And we have these different variations we can look at for different weather conditions that have, we have different observations for those different weather conditions. And so I'm going to choose from there and send them over to the operator so that we can start observing those. We have our actual queue here. And so this is where I actually control the observation. It's usually full of things. Right now it's pretty blank because we're not observing tonight, but that's where that's going to take place. I can monitor instruments in the top, this far left top and bottom plot over here. Number of different windows here showing the state, the condition of 3 of our different instruments that are on the telescope right now. And then down here in the center or bottom left is my observing tool, the same piece of software that Brian was showing you, but set up so that the observer can use that to run the observations. And then on top of that, I've got a couple more screens over here that are that I'm using to keep my night logs so that we keep a regular record of all of the things that are taking place, all of the events, all of the observations. We keep an accurate, detailed note so that the scientists can know what the conditions were for their observations, so that the instrument scientists, the engineers, can learn what kind of things went wrong, what kind of equipment they want to take a look at during the next day. So that's basically what the observer console is looking like. The operator console is kind of similarly laid out, but it's going to be much more focused toward control of the telescope. So they're not going to have certain of these some of the windows they will still have, others they will not. They'll have different things up instead. We try to backstop each other, so it's not just one person doing one task, but 2 sets of eyes on everything, essentially, because you can't afford to make mistakes with a piece of equipment like this. And with people's research, we want to give them the best data that we possibly can.
But Charlie, what if a mistake happens?
And mistakes do happen.
God, really?
Only with your data, Brian.
Okay.
So I'd say the most common mistake that happens is that the weather conditions change, and so they go out of spec. So each observation has a required set of weather conditions. This observer wants absolutely perfectly clear skies. They want the best possible seeing image quality. This other observer doesn't need it quite as good as that. And so because weather is variable here, sometimes we'll have night and the weather conditions just stay the same every night. And I can sit here and go right down one queue and just do the observations one after the other. On a night like last night, the weather conditions were changing drastically and rapidly. So I'd be in the middle of an observation that was taking advantage of really clear skies. And then all of a sudden the skies weren't so clear. And I had to stop that observation and mark that observation as essentially as not of that highest quality that we expect, and switch over to a different program. Because if we kept doing that, then this researcher would not get the kind of data that they need. We'd be wasting time. So as far as mistakes go, that's sort of the biggest, it's not exactly a mistake. It's just one of the biggest things where we have to go back and fix things because we went out of spec. But sometimes you make mistakes, we have problems, we document them, and we have a lot of manuals, we have a lot of reference pages. When things happen that shouldn't have happened, we try to make sure that we do better training next time, we make amends. We don't get in trouble. We know we're all trying very hard to do the right thing.
I think that's a really important part to really share, because we're humans, and it's working together as a team. Inevitably, something is going to happen where we make some kind of error, and for the scientists to understand that, of course, that was not intentional.
Absolutely. It's part of the trust. It leads to an environment of trust, so that I know that I've made a mistake. I know I'm not going to get yelled at, but I know I can come clean. I can say, look, here is a problem with this. Can't use this data. I don't trust this data. And in fact, that's part of one of my roles as the observer, is to evaluate the data and say, this data is what you're looking for. It may not have the answers that you're looking for, but that's not because we collected the wrong data, is because you asked for the wrong thing, and I can't help you on that front. And that does happen. But I think that environment of trust, I know that I can say, I screwed this up. And there's been cases where I had to come back the next day and say, I realized that I made a mistake in setting up this observation, and that hour-and-a-half observation, it's trash. It's not worth it. And I hate that. I feel terrible, but I also know I have absolute confidence that I can do that and learn from it, basically.
Amazing. Even just standing here listening to your explanation of what's on each of these 8 screens plus, it's still quite overwhelming. And so I'd imagine the training for each of the roles is pretty extensive.
It's extensive. We generally go through quite a few weeks of training before you get to solo, before you're doing the job on your own. There is but I think in almost every case, when you start training, you jump into it quick. You might sit in a chair by the side of the experienced professional the first night or part of the first night. But probably by the second night, you're going to be sitting in the chair, and you may not know what you're doing, but you're going to be talked through it. So, I mean, that's the way we work here, because I think everyone on our team knows that you learn best by doing it. I'm going to move the mouse around. I'm going to learn the patterns. I'm going to learn where things are much better than if I am watching somebody else do that. And I think that's a fairly common thing in many educational environments now. But we jump into training really feet first.
Wonderful.
So as soon as we can start training you up, Jamika, then you could be doing this job.
Ooh, I have to keep that in mind. I definitely love being here with you all, and I learned so much every time. Okay, so Charlie, I'm going to ask Charlie to click off my
I will click off
my camera
as soon as I can find it. That video.
Okay. And that was absolutely amazing to get a view there from your perspective.
Yeah.
But as Zach would be in a different role, you said you have some similar screens, but maybe a few that are different. Zach, what screens over there do you have?
I have no idea.
Oh, I'm so sorry.
So Zach and I would actually normally be in this chair, and Charlie's the master of both chairs. Yeah. Yeah. So
I need that on a t-shirt.
You should make a t-shirt.
I should make a t-shirt. So what's over there that's different? A lot more windows that are based on telescope systems. So we have different systems that are specific to each of the little components. This telescope is not a monolithic piece. There are multiple computers that are controlling each mirror in the telescope, that are controlling all of these different components in the telescope. So I can't even imagine, I have no idea how many computers we have up at the summit. But basically, all of those things are being controlled to the extent that they need to be interacted with. They're typically being controlled over there. The operator is going to be largely making sure that all the equipment is working the way that it should be, that the telescope, the instruments, the dome, the enclosure itself, that it's rotating correctly, that the shutter is moving the way that it should. They're going to be opening and closing vent gates to make sure we have the right kind of air circulation through the dome, because if the air gets stuffy in the dome, that will degrade the image quality, or degrade the data that we're trying to collect. So they're going to be taking care of all of that. They're going to be responsible for actually moving the telescope, for setting up guiding. So they have a lot more windows there that are specifically aimed at monitoring all these subsystems and making sure everything is working. It's a big job just to keep an eye on everything. You start to learn, tricks and just the rhythm of things, so you can tell when something's going wrong. And we have lots of different alarms that'll tell us when something's going wrong as well. But the experienced operators can tell before the alarm goes off that something is not right. And so that's mostly what's going to be over there. So the operator is in charge of the telescope itself. The observer is more in charge of the science, which is why we can let people like Brian or Zach sit over in this chair sometimes. We don't trust them with the telescope.
Right. We're not trustworthy characters. That's great. But so yeah, I think I would add to that again, so with all the different roles there are here. So it's not on Charlie, so for example, Charlie mentioned a potential mistake that he might make or I might make during the night on the observer role or the operator role. This is it's very complex. There's a lot of different things happening. We have to juggle different things. And so each role, in the observer chair, you're concentrating a lot on the science that's being done and the conditions and trying to match the observations to the conditions to get the most science out in a given night. But before that, as I mentioned previously, so Zach's role, one of the things that he does at the observatory, one of the things that I do at the observatory is make sure that the observations are well matched to the science. So it may be that somebody who has very little observing experience proposes and they have a really wonderful idea, super cool idea. I want to observe this black hole in this such and such way. And, I'm asking this particular science question about this. And so we say, that's a great idea, but we've actually, spent a lot of time on the telescope. Maybe we can suggest to you that you may want to observe it in this way instead of the exact way that you said. And so part of our role here is to shepherd scientists that propose these observations to a place where they might get the most out of the observations, so that when we get in these chairs, we don't have to think so much about, okay, is this exactly right for the science? We have everything prepared, nice and set up. But still on this side of the room, we have somebody that's trained scientifically to be able to say, oh, that doesn't maybe look that right, even though, because we can make mistakes during the day, we can overlook things. There's a huge number of moving parts here. And so we have several layers of gatekeeping that happens. And so because you're concentrating on the science output on this side, and you should be concentrating on the science output, you should be trying to get maximal science output for the given amount of time that you have on sky and the conditions. We're not to be trusted because that's where our head is. That's where we're supposed to be concentrating on. And it's the counterweight of the operator over there to say, no, you can't do that. And we say, okay, so now I have to think of a different set of observations. So we have all these different counterweights, people with very different backgrounds that are giving their perspective, and they're told in this given moment, you concentrate on this thing. This is your role, and you're well equipped for this role. You're well trained for this role. And then we pass that off to somebody else, or we use it in real time, we're used as a counterweight, a foil to somebody else. And so that's one of the amazing parts of the observatory. And we all share these roles in some way, and to the limits of our capabilities, of our training, of our background. And so we have these bridges where we can say, I know what Charlie's doing right now. And so I can interact with Charlie, knowing my role over here as a, kind of like daytime science guardian, to
Also,
Charlie as
t-shirt.
the nighttime science guardian, master of two chairs.
Master of two chairs. Well, and I think if I could follow up on that, during the night, it's largely just us, the operator and the observer. If everything's going right, it's just us. But I know that the reason that I can sit in this chair and do the job is that I've got people like Brian and Zach, who are doing exactly as Brian mentioned. They're preparing everything. They're working with the actual researchers to make sure that we are setting up their observations in the best way possible. I could not do this job if they weren't doing that one. In a similar way, the operator is sitting there and they know that the reason that they can do that is they have people like Garema over here who are making sure that the equipment is working the way that it should, that the adaptive optics is working the way that it should. And there are times when things go wrong, and we will call a contact scientist in the middle of the night to say, there's an issue with this program and I'm not ready to abandon it. I want to try to see if we can fix it here on the fly, and we'll contact them. Or something will go wrong with one of the instruments, and we will call the instrument team point of contact. And in fact, last night we did that, and the poor fellow actually came in twice, once in the earlier evening and then once at 1 o'clock in the morning. And bless him, he stayed here for a number of hours each time to help try to get things working again, because sometimes things go wrong. But it's that teamwork. I mean, I think we have a little bit of good nature, and it's not even rivalry, but just joking, adding back and forth at each other, but really is a team. We could not do something like what we do just one person or just one team. It's a huge effort, and we work together and we trust each other to do the job.
Amazing. I do love how absolutely essential collaboration is to make any kind of science happen, but especially as we're talking about astronomy, absolutely essential and vital. And that really leads also into, communication skills, being able to identify what exactly it is, what exactly the issue is, so that when you do reach out to, I think you said, a contact scientist or the instrument scientist, they have at least some place to start.
Right.
And so when you talked about instrument scientists, Garima mentioned, did you mention DPI too, or am I just pretending that you said that? You talked about, you are an instrument scientist, right? You work on one of the particular instruments that will be on this telescope soon-ish.
That's correct.
And so as the instrument scientist this is the Gemini Planet Imager 2, yes. And so as the instrument scientists that are on the team, if we're all here observing and we're really excited, got things going, the instrument is running perfectly, and then there's a hiccup. And we have you on speed dial, Garima, and we need some help. What do you do? How do you start that?
So, well, I joined Gemini just a year ago, and I've had the opportunity to fix. But I think I can tell maybe from especially with the adaptive optic system, like when something goes wrong, like when an adaptive optic system is not doing what it's supposed to do, then what kind of things you need to do, what kind of checks you need to do during the nighttime. And I think maybe I should talk a little bit about adaptive optics.
Yes,
How would it be?
please. Yes, please.
Maybe I can share my screen.
Yes, you should be able to do so.
Somebody mentioned in the chat it's a little bit hard to hear.
Oh, I see.
if you have
Okay.
a projector.
Maybe I can sit a little bit closer.
So again, adaptive optics helps to compensate for the distortion and the distortion caused by Earth's atmosphere, the distortion that we could potentially see in an image caused by Earth's atmosphere. AO is short for adaptive optics. Wow.
So basically what happens, maybe I can, this is one of the slides from some talk. So when the light from star and planetary system, it traverses the Earth atmosphere, the light basically meets layers of different temperature and pressure and wind speed, and basically it causes the change of refractive index of the light. So instead of seeing a very nice stable image of a star, we kind of see a fuzzy blob. And twinkling is another effect because of the atmospheric turbulence. And so the job for the role of adaptive optics is to basically undo the twinkling effect and make sure that the image of a star is as stable as possible on the science camera or science detector. So there's a video by Gemini actually of the adaptive optics, like how does it work? So maybe I can just play that video. So when the light basically enters the instrument, an adaptive optics instrument, I'm gonna just pause here and then basically tell you, maybe I can just keep playing it. The light basically go into different optics within the instrument, and this is what you see, the image of a star. So I'm gonna pause here, and what you would notice here is it's not a nice stable image. What you see is a fuzzy blob, which is really moving fast. So the role of adaptive optics is basically to undo the effect of the Earth's atmosphere and create a stable image. So what happens is basically in this video, you have like the wavefront of light, which is all like twisted. And so in adaptive optics, we have a sensor, wavefront sensor, which senses the amount of aberration in your system. Sorry, in the amount of aberration introduced by the atmosphere. And then we have another optical element called deformable mirror, which basically corrects for those aberrations. So this deformable mirror is just a thin piece of glass, which is supported by a bunch of actuators, and it straightens out the wavefront. So once you have like this AO adaptive optics working, and your wavefront sensors, they're sensing the aberration, and deformable mirror is correcting for those aberrations, what you see is a nice stable image of a star. So that's what adaptive optics does. So when Charlie was saying, like, let's say something goes wrong in the middle of the night, and let's say adaptive optics is not doing what it's supposed to do, then people like me receive a call, and then it's our job to basically understand what's happening basically. Is it something optically? Is it something inside the instrument which is causing the adaptive optics to not work? Or is it a mechanical issue? So sometimes we are not able to solve those problems during the night, so we fix it during daytime. So we have like this daily meeting, 9:30 meetings, where everybody discuss what went wrong, and then each one of us is basically being assigned, the job to basically fix it, so that during the next night, the solution, we have the solution, and then the AO, for example, in this case, is working and producing best image possible.
Incredible. This visualization was very helpful. We had a request, Garima, in the chat, if it were possible to get a link to these incredible slides.
Link. Oh, okay. This is actually the talk that I gave on exoplanets, so I can share, definitely. I can share these slides with everybody. Maybe I'll share it with you, and then you can.
And then I can send it.
Sure.
Yeah,
Okay.
absolutely. So yes, we will definitely get these slides from Garima. Thank you so much, Garima. And then I will make sure that all of the teachers receive a link. Thank you so much for that. So, time here, about half an hour left. Several things we want to touch on in this last half hour, and you all keep dropping those comments and questions in the chat. Zach, Brian, we are going to be busy answering them as we continue to go through this last half hour. It's just been so much fun and amazing and informative, even for me, even though I've had the opportunity to be here shadowing this team quite a few times. I love and am so appreciative that I get to learn new things all the time. So, struggles with research.
Yeah, so there was a question in the chat. I don't think that we got a chance to answer yet. Risha asked about sharing a challenging or memorable moment from a research journey. So from our path, younger years all the way to the point that we're Gemini controller now. I'd actually like to invite you to share. So see how is your research journey? Nice and smooth, easy, everything's fine.
We don't usually talk about me.
Yeah, try the tables a
They
little bit.
put me on the spot here. It's not normal. I'm very happy to answer that. No, my journey has been not at all linear. It's been very circuitous, full of adventure. I am really thankful to say that I've had the opportunity to intern at the Canada-France-Hawaii telescope. This is very near Gemini on the
Right next
eastern
door.
ridge. It's right
Right
next
next
door.
Just north of us.
Yes. Okay. And while I was there, this was maybe 5 years ago. And while I was there, I had the pleasure of interning under Dr. Andrea Patrick. And I'm very, very grateful to the then director, Dr. Doug Simons, for that opportunity. I was doing, like Charlie, doing some, not like Charlie, but doing radio, using some radio data, just the tip of the iceberg, getting my feet wet, so to speak. And it was amazing. Radio astronomy is so different than optical astronomy, than infrared astronomy, than anything else. And I found it actually quite wonderfully challenging to understand how to interpret the radio data. And I was working on quasar evolution. And from that experience, and I had great guidance, so many opportunities with the CFHT staff. They were very supportive and always answered my questions. And in particular, Dr. Andrea Patrick was an amazing mentor. And even just most recently, last week, we were at the American Astronomical Society. Charlie and Zach were there, and Dr. Andrea Patrick, although I missed her, was also there, and we connected just yesterday via text about the research that she and her amazing team continue to do. And so what I learned there from my experience was that while I enjoy extragalactic research and these, incredible events that are happening and trying to get insights into things that we could never imagine seeing right here in our local galaxy, our local universe, our local solar system. I mean, I realized I did want that. I do want to look at things that are a little bit closer. Galaxies are amazing, but what's within our own galaxy, and even closer, comets, asteroids, what's going on in our solar system. And so my research interests have really narrowed, and I'm happy about that because I'm now focusing on planetary sciences and actually particularly geology, astrogeology, as Charlie was just speaking about. Like you all, I am in school working on my third degree, and has been an amazing adventure, and it's thanks to amazing colleagues and just wonderful humans like the ones that you see here in this room that have kept me inspired and that have encouraged me, that have shared their knowledge and showed me things about myself that I didn't even realize that has really been absolutely incredible. And so while right now I'm so honored to serve as the coordinator for Shadow of the Scientist, I am getting an education in every session, just like you all. So I'm continuing my studies, and that certainly includes spending time with these amazing scientists, Brian, Garima, Zach, and Charlie. How about that response,
That was
Brian?
great. That was awesome. Thank you, Jamika.
Thank you, thank you. I'm gonna toss it back to you.
Yeah.
Yes.
Does anybody else want to like share, I don't know, struggles, bumps, triumphs during their path here? I'm happy to share some of my journey. Yeah, so I started as a kind of punk high school student. So I was in high school, I was very bored by school. I didn't really like school. I wasn't really motivated to learn. I didn't understand why I should learn the things that people were telling me I should learn. I didn't have teachers that were particularly motivating. Where I came from, it was kind of assumed that everybody wanted to go to university, that everybody wanted to get the best grades possible. And I never really saw it. So I failed out of high school, and I then went to boarding school in the upper part of the state of Idaho, into a very rural area, town of about 400 people. Where I got to spend a lot of time with the stars. So it was doing a lot of like, at first it was doing a lot of manual labor, and then it was trying to figure out what exactly my motivation was. And so I had a lot of time by myself, a lot of time with the stars. And I realized that maybe trying to do something really, really challenging that constantly humbles me or even humiliates me is something that is very good for my soul. And to constantly be put in a position where I don't know and to be surprised by things is something that I crave. That's something that I crave as a person. And so I thought, okay, what could like be the most humbling discipline that I might want to get into? And so the two things that came to mind were religious studies and astrophysics. And I thought, okay, I'm like sitting at math, so maybe I'll try for astrophysics. And so I just started trying that. So I went to a community college, which is an academic institution in the United States, which effectively allows a degree if they have some interest and it's financially backed, so you can get in and you can don't have to pay a bunch of money and you can get a decent education. And I was fortunate enough to go to a good university after that had a very good astrophysics program, which is the University of California, Santa Cruz, which is where I met Raja Guhannakurta, who's the leader of the Shadow of the Scientists initiative. And he was incredibly inspiring for me as an undergraduate, trying to understand my place in the research world, how I might take some of the very naive ideas I had about astrophysics and morph them into interesting questions about the universe. And so it was my first interaction with Maunakea was with Raja back in 2003. Was my first observing session on tech. And over the last 20 years, I've continued to temper those scientific questions. I've had the privilege of using many of the telescopes on Maunakea, using Hubble, using James Webb, to answer, or at least attempt to answer some of the scientific questions that I have. But I have never regretted that decision to go into this discipline. The universe is endlessly imaginative and constantly surprises me, constantly challenges me, constantly makes me look like a fool, and I absolutely adore that. So that was my journey.
Incredible. First, there were a few things there that I actually didn't realize, and I'm so grateful that you shared that. One thing though is the community the community college piece, and even before that, not being fully interested in school because it wasn't quite engaging for you, and really sharing that even though maybe you have that kind of start, because I certainly, when I was younger, before getting into university, had some struggles before getting there. I had to get my grades better, do more studying. I had to get tutors, and while Brian said that he was pretty decent at math, I really liked math, but I found it a bit challenging to approach the upper level math. And I was so grateful that I had teachers around me who continued to encourage me, because I was definitely stumbling. And that support system being there was a blessing. But I had to reach out and talk to my teachers, like your amazing teachers who are bringing you to this session with us right now. I reached out to my teachers and let them know what was going on. And that was the only way I was really able to get back on track and not lose my focus. So thank you.
This is very common. This is very common amongst astrophysicists and scientists in general. I mean, the paths are never linear. People come from all different backgrounds. It's crazy. It's a crazy endeavor, what we're trying to do, and it requires crazy people. And so yeah, no two paths are the same, and everybody struggles. I mean, yeah, I was decent in math, but I mean, there was many subjects that were, really challenging for me. And even, I can say, okay, conceptually, I can work my way through at least some of the scientific endeavors that I'm involved in research-wise, but then we get challenged here with doing an observation of a supernovae, which I don't necessarily know that much about, or supporting a scientific program that's looking at accretion onto a white dwarf, which I may not know so much about. So it really pushes and challenges us to constantly be adaptable, constantly try to learn, and that, I mean, it's a lifelong journey. And if you're not here to learn, you're here for the wrong reasons. and if you're not listening to what the universe has to tell you, it's unfortunate.
Yes.
I don't want to diminish if anybody else wants to share their story, but I know we have some data that we might want to show at some point. But if anybody else wants to share.
I certainly could share a little bit of mine, because I think just echoing the very much it's a non-linear journey. I mean, I knew that I loved physics, I loved astronomy, very young age. And sort of the first thing I remember saying, when I thought about what I wanted to be when I grew up was, I wanted to be involved in some of the programs that took, I mean, at a very, like an age of 8 or so, I knew that I wanted to be involved in some of the missions that were putting landers on different planets, for example. And I did not go that way. I mean, I went into physics, I went into astronomy, I studied those things. I went to grad school, and I still did not know exactly what I wanted to do. And I was taking courses in the two things that interested me most, in laser optics and in astronomy. I ended up getting my my PhD in laser optics, kind of almost on a random chance. I had a very good, I fell in with a very good thesis advisor. And I realized that during that process that I loved research, but I also really wanted to teach. And so I ended up getting a position out of grad school teaching, with the intent that I was going to continue the research work that I'd been doing. And what I realized is the institution I was at, there's no way to continue the research. I was at a smaller school, and there was just no time. I was teaching too many courses a year. And my research would have just completely withered away and died, but I fell into a group of radio astronomers, which is kind of like falling into a biker gang. And I actually made use of my astronomy, the background that I had in this astronomical courses, astronomy courses, astrophysics, and was able to be a contributing member of a couple of different research groups studying massive star formation. And I was able to do that, sort of work that into the corners in whatever little bits of free time that I could eke out. And then finally, I decided to take a different direction, left formal teaching, and came here, and it's been an amazing experience. And I think the thing I'd point out is it's, I think it's kind of been said so far, it's never too late to try something new. And it's always worth it to try something new, even if that goes poorly. I think it's worth it. So that's my nonlinear experience.
Thank you for sharing, John.
Absolutely. Before we jump into our last little bit, Garima or Zach, would you like to share any aspect of your experiences, triumphs, or any bright said bumps in the road? I have to say, I'm particularly interested with Garima because you did you went to school in several different countries.
Yeah, I have a lot to say, but maybe I can say maybe just a few things, to respect the time. Well, I wanted to study stars and planets when I was a little girl back in India. And I think a lot of people probably on the call might relate with me because my family was not very educated, so they had no idea what I wanted to do. And there was a lot of opposition from my family against my education. So I had to kind of work hard and fight with my family, and mostly with the ignorance that they had, just because they had no idea what I was talking about. I had no idea what I was talking about when I would say I want to study stars and planets. And where I come from, it's more like they thought it was astrology, and I'm like, it's not astrology, it's astronomy. So I had to kind of work very hard. I had to create my own path from the very beginning of my childhood, basically. And I did my bachelor's in information technology, nothing, not at all related with astronomy, just because this is what everybody else was doing in my neighborhood. And my parents were like, you're a woman, you're a girl, just go do what others are doing. And, once you're done with your bachelor's, you can, find a job and then find a man and get married. Basically, that's the plan. That unfortunately, that's how it is back in India, especially in my time. So I had to fight with my culture, with my, I had big dreams. So after my bachelor's, I actually changed my field. So I went to France to do my master's in French, and I did not know French. So I learned French while I was learning astronomy in a different country. That's how I began my journey. That was during my master's, and I've gone through that was the beginning of a lot of challenges as a brown woman in education, and I've experienced a little bit of racism, a little bit of a bit of sexism, a little bit of belittling, just because I came from a different country, didn't speak the language, didn't even speak astronomy language. So there was a lot of hurdles. So, but something I can say, I always told myself why I'm doing certain things, and I didn't care about how. So that was my way of self-motivating myself. As long as I'm clear about why, I didn't care about how it's gonna happen. So that was a bit difficult, but I kept moving on, and I did my PhD between France and the US. And my dream was to actually work for NASA. That's what I wanted to do when I was a small girl. And I was able to work for NASA for 2 years after my PhD. So I worked at JPL. That's when I was like,
Incredible.
so this that has been a difficult journey, but I think I'm gonna stop here because I want to respect the time. But it's not only about me following my dreams, but at the same time, I had to fight with the culture, and then with my own culture first, and then with a different culture. And then the fight is still on because, there are not a lot of women who do instrumentation, and not a lot of women who do exoplanet instrumentation. So it's still, there's always a struggle, just the face of the struggle is different. And the idea is just to kind of I still follow the same thing. I want to have one thing clear in my head. Why am I doing this? Why? If that's clear, then I don't care about anything else.
Amazing.
So I'll stop here.
Wow. Wow, thank you for sharing your email. I did not.
There you are.
And Zach, we don't want to leave you out. Do you have anything to share before we close with Charlie? Zach.
Not really. I mean, I'm interested to hear about Cycloid. First time I think I'm gonna see it in action.
Oh,
Seriously?
Oh, okay,
Yeah.
okay. Charlie,
I haven't observed in like 4 months. So let's see some Gemini data.
All right,
With some data from the universe.
All right, so I'm going to share my screen here. Let's do this. Got to share. All right, so this is one of the pieces of software that we use. This is a fairly new piece of software that we use as an observer, first and foremost as an observer during the night. As we collect data, we want to take a look at it. We want to make sure that we're collecting the best quality data that we can for the researcher. And I'll show you just a few images here and talk a little bit about this piece of software. I have a very close association with this. I'm basically responsible for putting this together for us. It's not entirely, it's not all of my own code. It's based on a viewer, a data viewer that was created by a fellow over at the Subaru Observatory, just a couple of buildings down on our street here. Excuse me. What you see here is a false color image taken by our GMOS detector. And so you see a nice star field here. GMOS is a fairly complicated detector in that it's actually made of 3 different CCDs. You can see those as 3 different panels here separated by a narrow block. And as data is written to our data archive, this program is going to say, oh, a new data file is written. It's going to automatically load that up and show it to us as quickly as possible so we can review it and make changes if they need to be made. If we see that some of the stars are saturating, and in fact, you can see here that, you know, there's this little bit of red dot in the middle of a couple of these stars. Those are stars that have saturated. There's too much signal, and and that's typically not good. Now, depending on the science, depending on what the actual target is, it's okay to have a few things saturate like this. In this particular case, the object of interest was down here, one of the faint objects toward the center of the screen, so we're not too worried about a little bit of saturation in some of those brighter things. One of the interesting things I want to draw your attention to, because it's kind of pretty in this data set, let me open up a little zoom window here. This is going to magnify everything so I can, you know, as I move around, you can see a magnified image. I'm going to come up here to the upper right, and you'll see this kind of elongated structure. And you might be able to see that there's some arms on that. There's a nice spiral galaxy there that we can see. That little bright line right kind of near the middle of it is an artifact that is probably a bit of cosmic ray or something else like that. That's not real. But this is an example of an image. It's a false color image here. This image is just essentially is a single color image. I like to choose this is just a color map that I have chosen because that makes it easy to see certain contrasts. And this color map tends to be very friendly to colorblind individuals as well. And so I try to make this, when I was coding this up, I wanted to make it as accessible as possible. I'm going to show you a little bit here about what I can kind of demonstrate a little bit about what that observing process looks like. So one of the first things we do is we're going to take a quick image, a quick series of images called acquisition images. And those acquisition images are going to make sure that we are lined up on the right target. So this is the first image of an acquisition image. It's what we call a field image, and it's going to basically show us the actual bit of space that we see there. And so we can look at this image and we see a bunch of stars and this big oblong smear across that. There's something bright that's nice and long there. And that's a real thing. That's not an artifact. That's not a cosmic ray. There's something big and elongated like that. It's kind of hard to tell exactly what it is, but I can use this software to give me a little bit of a clue. And so what I'm going to do is I'm going to adjust the contrast levels. I'm going to adjust the high and low values here a little bit. And now I can look at this and in fact, I'm just going to zoom in on the main window here. And there again, you can see some spiral arms. This is a close to edge on this galaxy. So you can see the galactic nucleus right there. You can see those arms stretching out and some dark areas of dust lanes. And again, there's a cosmic ray. There's some kind of noise artifact, that sharp line there. But what's particularly interesting in this image is really, I mean, as pretty as the galaxy is, that's really not the target of this observation. The target of this observation is this thing right here. Now, I want to point out really quickly, when you look at the rest of this image, all of these stars, all of the things in this image that are stars, those are foreground stars. Those are stars in our own galaxy. Those are not stars out in the universe. They are here in our own galaxy, up close. But this bright object right here is actually something in the disk of that galaxy. And that object is about as bright as the nucleus, the core of that galaxy. This is a supernova. So if you had imaged this galaxy a month earlier, you would not have seen that. It wouldn't be there. We mentioned earlier on that, galaxies don't tend to change much in human lifetimes, but this is a case where sometimes things happen quickly. A star explodes, there'll be this bright afterglow that'll last a month or two, and it'll slowly fade out. And this was an early catch of that supernova. And I think one of the things I really like about my software is the ease at which it is to find that, to see that. We point to that part of the sky. When we first take the image, the raw image looks like this, but very quickly my software can go and allow you to adjust and see that target very, very fast. Now, what happens is from the observing role, I know that what I want to do is I want to line up that supernova with our spectrometer. I need to get it lined up in exactly the right spot so the spectrometer can break that light up into the different wavelengths, and we can look and see what kind of elements might be present in the supernova material, so we can learn the most we can out of that. So we take this field image to make sure we know where that is. We take the next image, which is an image of the slit itself. So we know that's what the slit looks like that the light has to pass through in the instrument. So this thing is essentially this little slit-shaped window in the instrument itself. And then we line them up. So here, and I'm going to do that little adjustment on the brightness again. You can still see that slit stretching up and down in the frame, but you can see the brightness. That is that supernova. You can't see the galaxy here. The slit is blocking out all the light of that galaxy. We are just focused on that supernova. And then once we've got everything lined up, we had to do another adjustment, and then we can start collecting data. And so this is an example of the actual spectral data. Once we got that lined up, this is GMOS long slit data. So these bright lines that you see running vertically, those are spectral lines corresponding to different elements in that. And in fact, we can take a little bit of a different view of this, and we can see, let's see if I can make this work. And for some reason, well, that's interesting. It's not working. Why isn't it working? All right, well, I'm not sure why that's not working. That should have given us a plot. That's the first time that hasn't worked, and I need to go and do some debugging. But basically, the researcher is going to take this image, and we're going to take multiple images like this and add them together, average them, sum them to make sure that we can bring out all these very faint lines, in here. If I adjust, you can see that there's a lot of stuff here that you might not be able to see at first glance. But the software that I wrote helps us as observers look at the data and understand what the data is telling us, make sure that the data is the highest quality. And again, here in this image, you can see lots of like snow all over the place here. Those are cosmic rays again. High energy particles that hit our atmosphere from the cosmos, from the universe, and they will essentially expose the detector. And we can see those here.
What an incredible way to wrap up this special session. I know we're just at the end of your time. Thank you all so much, teachers, students, for joining us. Charlie, that was absolutely amazing, absolutely amazing. And Brian has dropped in the chat where you can download the observations of that supernova. I'd like to just thank everyone in this room, Garima, Zach, Charlie, and Brian. Brian is really a champion of this initiative, being able to enable us to share not only all these amazing people and the roles that they do, but the science that comes out of Gemini Observatory because of the amazing collaborations that they do. Thank you all so much for being with us. Thank you for these amazing questions. And yes, I see again a request for those slides from Garima. Yes, absolutely. And Garima, what you were sharing was just been so inspiring and so it resonated so well with many in the chat. So thank you all again for sharing. And my name is Jamika Marshall. It's been my pleasure to host you this evening as we shadowed the astronomers here at the International Gemini Observatory North, the Hilo Base Facility here on the Big Island of Hawaii. I will definitely be following up with you all in the next few days, not only with Garima's slides, but also a follow-up survey. And we look forward to having you all back here in the Gemini control room virtually sometime in the near future. Thank you so much and have a fantastic rest of your school day. Thank you so much, teachers. Aloha.
Aloha. Thank you.
Aloha.